So don't be afraid of any complex math in this video because I'm in middle school and don't have the necessary math skills to explain that. So instead I'll just be explaining the core concepts of calculus and how they apply to understanding how rockets work. So what is calculus exactly? Calculus is a method developed by Isaac Newton that can be used to solve many different engineering problems that cannot be solved using normal math. So for example, here we have the position of a ball over time. The position is represented by y here. And its path when thrown in the air makes an arc, like this. So let's say we wanted to find the average speed that the ball is going on this half of the arc. Well, then we would just take this distance, the total y, divided by this time, the total time, or delta y over delta t. But now let's say, what if we wanted to find the velocity at a single point during this arc? Well, we can try to approximate it by making a smaller average that we would be from t1 to t2 and from y1 to y2, and you could write that as y2 minus y1 over t2 minus t1. Same thing, this delta. And we could keep getting smaller and smaller and smaller until each side of this triangle here is infinitely small and we actually get to this point. So each side here would be what we call dy and dt, a tiny infinitesimal size. And if you draw the curve on the outside of this little triangle, it would be an exact straight line, not a curve. It would be a straight line. This means that the speed or velocity of the ball at any point during this arc is the slope of that point. So the slope at any point during this curve would be dy over dt. And here, the slope is very steep, which means the ball is going very quickly. But over here, the slope is 0. It's completely flat at this point, at the top of the arc. So its velocity is 0. And when it's coming down, it's negative, but it's still increasing and going faster because the slope is getting steeper and steeper. This is what we call the first derivative of y, or basically just the rate of change of y at any point. Okay, so that's derivative, but let's try to find the derivative of this parabola. We know that a parabola is the y value is a certain function of x, which is ax squared plus bx plus c. Now we can go to a derivation table like this that gives us solutions for different derivations. And we can see here that there's an x squared, so there's an x to a certain power. And on the table, we can see here that there's the solution for the derivative of x to a power, and that is n times x to the n minus 1. So x squared is 2x to the n minus 1, which is 1. So this just becomes 2x times a, which we can rewrite as 2ax, plus b, and no x because x is just x to the 1. 1 minus 1 is 0. So anything to the power of 0 is 1. So this is b times 1, so just b, plus c, and c is a constant, and the derivative of a constant is just 0, because a constant doesn't change at all with time. There's no derivative. So we're left with 2ax plus b. And this doesn't have any exponents in it, so it's just the function of a straight line, which can basically just represent the slope of any point during this curve. And the plot of the velocity would just look like this, because in this graph, the velocity goes down and down and down and down, and then becomes 0 at the top, and then you start speeding up again when you come down, but it's negative because we're just going the opposite direction. B is the y-intercept here, because anything that's multiplying x is the function, and then plus b is where it intercepts. So this point here is b, and 2a is the slope of this curve. So now let's say we want to derive this again. So we would be taking the rate of change of the velocity over time. So this would be the acceleration of the ball. And that's just 2a, because we already know that an x by itself, according to this rule, just goes away. And plus 0 again, because b is a constant, and the derivative of a constant is just 0. So we're left with 2a. So this tells us that the acceleration is constant, because a is a constant, and 2 times a constant is still a constant. So the acceleration of a plot of acceleration would just look like this, a straight line. And that makes sense, because this object is like falling through the air, so gravity is the only force acting upon it, and gravity does not change with time. And gravity is an acceleration, so this graph makes total sense. So in summary, in the case of physics, y, or position, its first derivative would be velocity, which can be notated as y dot, and the derivative of that would be acceleration, which can be notated as y double dot. So this was a small introduction to derivative, which is very useful in finding the instantaneous rate of change of anything. For example, in this video, we were able to find the acceleration and velocity of a ball given its position over time. Thanks for watching, and I hope this was helpful. Next video, we will be talking about integrals. Please make sure to check out my videos on rockets and rocket thrust, etc., and to like, share, and subscribe.